this interesting workshop, perhaps, but unfortunately I'm in Japan, and so this is a late time in the evening already, so I don't think I can attend the second session in the afternoon. But anyway, today let me talk about this sort of recently kind of becoming a hot topic about primordial black holes and its relation to gravitational wave cosmology. And today, especially, I want to focus on this role of isocurvature, so-called isocurvature perturbations, which have not been discussed much until recently. So let me go on. Do you see my cursor, by the way?
Yes, we can see it.
Okay. So first of all, let me just briefly review the sort of standard scenario based on the curvature perturbation and most probably generated from inflation. So you have this kind of a famous a space-time or time-space diagram. On the horizontal axis, you have the log of the E-fold number, or the log of the scale factor of the universe. And the vertical axis is just log of the length scale. Then expansion of the universe just goes along the linear sort of a line, proportional to the scale factor. What we actually have observed in CMB or large-scale structure observations and so on and so forth are on this fairly large scale, so-called, let's say, a few gigaparsec down to maybe 100 megaparsec, maybe 1 megaparsec. Now, some very large, so-called large scale. And on large scale, we have very strong constraint. For example, Planck data constrains the power spectrum of the initial curvature, so-called curvature perturbations, which essentially are gravitational potential perturbations, which gives rise to all the structures in the universe. While if you go down, say, 20, 30 volts to a smaller scale, which corresponds to, let's say, parsec scale or even smaller scales, then on those scales, we virtually have no constraints. And so this means that maybe there's a chance, and actually there are many inflationary models which predict that you may have some sharp peak in the power spectrum. And if there's a sharp peak in the power spectrum close to, say, let's say 10⁻² or so, then these fluctuations will be essentially frozen on scales greater than the horizon. But when they re-enter the horizon during, let's say, radiation dominance, we will form a primordial black hole if the amplitude is large enough. And this happens, actually the actual amplitude should be of order, say, 0.1 or 2 or maybe 5. But the fluctuation, mean square fluctuation would be maybe 10⁻² or so. So you have some, this means that the black hole which are formed will be a very sort of a tail part, large tail part of the large fluctuation. Therefore, the number of black holes should be small, but that's good because black holes, after they form, would behave like matter. And during radiation dominance, because the matter component, once they are formed, grows in proportion to the scale factor relative to the radiation energy. So if you produce too many black holes, our universe would be completely dominated by black holes, which is not the case. Therefore, this small suppression, exponential suppression, actually is favorable for this primordial black hole formation. So this is sort of a picture which tells this fact that, for example, in the standard inflationary model, you expect the probability distribution of the perturbation to be almost Gaussian, and this sort of mass variance, or which is proportional to essentially the amplitude of the power spectrum at particular wavelengths. Even if this is small, you have a small tail in Gaussian tail, which above a certain critical threshold above which the fluctuation is so large that it will form black holes. Now, if just assume that this sigma is much smaller than the critical value, then you can essentially approximate this amount of black hole produced, which usually use this Greek letter beta to express the fraction of energy which is which turned into a black hole at the time of formation, will be given essentially by exponential minus delta critical square over 2 sigma square. And in the early times, or maybe until maybe a few years ago, people thought that essentially this delta C would be 0.4 or so, which actually for small sigma suppresses this production of black hole really exponentially. But recent studies by those people and some other studies actually say that in this sort of approximation, maybe the critical value is maybe factor 2 smaller. If this is factor 2 smaller, then square is factor 4 smaller. This means exponentially expansion to the 4 times greater, larger, or smaller, larger, sorry, yes. So actually you may have a very large amount of primordial black hole formation for a very small sort of a power spectrum amplitude. So this actually gives you further sort of constraints on the amplitude of perturbations you, for example, want to produce right here. But anyway, these are not sort of well, I mean, this is still under sort of a study, so we cannot really say anything very definite. But the whole point is that there is some exponential dependence, and so a small change in the parameter, the amplitude of perturbation can change the amount of black holes considerably. But if you take from the other point of view, if you think that our universe has certain amount of primordial black holes, then it means that you sort of measure beta. Then even if you have some the error bar of say a order of a factor of 10 or so, this leads to a very, very small sort of error bar in the amplitude of curvature perturbation. So from that kind of say bottom-up type approach, actually it is good that you are fairly free from all this fine-tuning of models in that sense. I mean, from the top down, you have to fine-tune, but if you go approach from the other way, it's the other is correct. But anyway, so the current sort of constraint essentially, which I sort of put the constraints on the abundance of black holes from some data, which is at least it's sort of a half my prejudice, but which I trust. So on the very, so this is a mass, 10 to 34 gram is like 10 to 33, sorry, it's like a solar mass. Yeah, yes. And so this is a solar mass scale, and this is in terms of grams. And if you go to a small scales like 10 to 15, 16 grams, then this black hole is so small that if we trust the Hawking radiation, they must have evaporated by today. Or if they are just evaporating today, they would emit a large amount of gamma ray and so on and so forth. And because of that, we can constrain the amount of those black holes very severely. And this is the line which comes from this black hole evaporation. And the other part, the very, very large scale part, this is due to this very, very accurate measurement of the CMB spectrum. And if you have a very large black holes, then they would say have some accretions of photons and so on and so forth. And this would affect the spectrum of the spectrum, so the Planck spectrum of CMB. And the spectrum distortion would be too large if you have too many of those huge black holes. So this comes from CMB, and this line may change by a factor of 10 or so, but essentially this is what it is. And the other is the constraint in the middle comes from the gravitational lensing, micro lensing. And so this is sort of assumes that the primordial black holes are essentially randomly distributed in the same way as a cold dark matter. And in that case, now the recent all these nice telescope observations and so on, so they constrain the amount of primordial black holes considerably within this range, from about 1 solar mass down to say 10 to the minus 10 solar mass. But interestingly enough, below that scale and above this horizon Hawking evaporation limit, there are about 5 orders of magnitude free, sort of a constraint-free region. And this is because the wavelengths of the optical wavelengths by which you measure all this gravitational lensing becomes so large that the mass, so the spatial radius of black hole becomes so small that actually the photons will not feel the existence of the black hole because of this wavelength. So this means that we have nice window, and if we have some interesting model that to produce the primordial black holes of the amount which is close to the amount of say cold dark matter, then actually we may be able to explain everything by the primordial black holes without any need to say some WIMPs or anything, some particle physics models. Anyway, so and by the way, so another interesting region is the LIGO-Virgo black holes region, which actually, if you just assume the standard sort of a random formation of the primordial black hole, then already because of the rate of say black hole measured by LIGO and Virgo, which was just introduced by Alexandra, already constrains the amount of black holes very strongly. Anyway, so but again, this may be some of those LIGO-Virgo black holes may be primordial. So that's another interesting possibility. These can be actually tested by gravitational waves. It's of course you may have those binary black hole mergers, black hole gravitational waves, but apart from that, because the very reason why those primordial black holes were formed in the very early universe, coming from the fact that you have this some large curvature fluctuations. The large peaks of the curvature perturbation, which is large enough, would form primordial black holes, but most of the sort of regions, the amplitude of the curvature perturbation won't be so large. Then, when they enter the horizon, meaning when the wavelengths become shorter than the horizon, they just started to oscillate like sound wave, and these space-time oscillations would produce gravitational waves. This is the secondary gravitational waves, and it happens actually that if the cold dark matter is primordial black holes with say mass of about 10 to 20 grams, then those space-time oscillations would produce gravitational wave with frequency of 10 to minus 3 hertz, which is just exactly on the Lisa band. If some of those, or maybe all of LIGO-Virgo black holes are primordial, then the corresponding frequency for those curvature perturbation generated gravitational wave will be about 10 to minus 8 hertz, which is at the peak partial timing array band. So now all this sort of interesting range of primordial black holes, which may be able to detect it by other means, for example, in this case, we may be able to actually measure the by those gravitational wave from binary black hole mergers, and this it's not so easy to detect, but maybe actually can account for dark matter. Those models may be tested by gravitational waves, so that's a very interesting point. Now, so about already more than 10 years ago, this Saito Yokohama has actually did the sort of a quite similar computation that, for example, if you consider a 10 to 20 gram, a little bit smaller than what I consider, but 8 gram primordial black hole, which is essentially the dark matter of the universe, then they would cross their frequency would cross this VISA or the SIGO or BBO band. If the primordial black hole is 100, well, it can be 10 or 100. So it's sort of a couple of orders within the solar mass scale. Then, of course, even the amount of those black holes is small. In their case, for example, 10 minus 5, they can be detected by pulsar timing array. And actually, these days, just a couple of years ago, there was a very interesting paper by those people that if the primordial black holes are like black holes are primordial, then they are very strong already concerned by pulsar timing array data, and meaning that the probability distribution function perhaps should be non-Gaussian. Anyway, so far we have focused on those primordial adiabatic perturbations, which is the curvature perturbation. But how about the primordial isocurvature perturbation? Now, this is sort of turns to be very interesting because, in the early universe, maybe you have some kind of phase transitions or maybe formation of some compact object in the early universe. And those objects during the radiation dominance behave like matter. Now, if their distribution, I mean, is, if the formation is random, then their distribution should be inhomogeneous. Then this inhomogeneous, some of the inhomogeneous region may have density high enough to form black hole after those matter start to dominate the universe. So this is the early universe matter dominant scenario. Of course, you cannot have this matter dominance until today, so they must decay out anyway. So the assumption is that all these sort of objects which are formed would be a metastable and eventually decay out. But anyway, so this scenario is interesting because now actually even the isocurvature perturbation can generate all these primordial black holes. Now, in the linear theory, the isocurvature perturbation behavior has been studied long time ago. Well, this is our paper, but of course there are probably many other papers discuss this evolution. But the whole point is that if you consider some so-called the isocurvature perturbation, which is the difference between the matter perturbation density contrast minus E over force of the radiation density contrast, then this would say be zero for adiabatic perturbations, but this would be finite and almost constant in time in the early universe. Now, if these perturbations wavelengths are much larger than the horizon scale when the matter becomes dominant, then essentially you have a very result which is sort of similar to the result is the initial curvature perturbation of the amplitude, say this 1/3 of S. This is the curvature perturbation amplitude, and in this case you have some density perturbation during this matter dominance, which behaves like scale factor, proportional to scale factor. R is the A over A equal time. Now, so in this case, although it has not been studied in detail yet, probably black hole will be formed if this S is greater than some value which is over 1. And but this needs to be studied. But this is a linear theory sort of thing which is very easy to do. The interesting or important case is the case of the omega much greater than 1, which means that those fluctuations, which is well inside the horizon already during the radiation dominance. In this case, isocurvature perturbation still remains almost constant, but the density perturbation slowly increase like again proportional to scale factor, because the matter density is becoming more and more important and start to dominate the universe. In this case, apart from this the small 3/2 sort of correction factor, the growth is essentially the same. So the perturbation in the density perturbation grows like S times some scale factor, which is just scale factor normalized at equal time. The point is that because the scale is so small, the curvature perturbation or the gravitational potential perturbation is suppressed by this 1/omega square. So if you assume that the primordial black hole should be formed at by this curvature perturbation to become order 1, then this requires S to be much greater than 1. This is a highly nonlinear initial condition. And in the early universe, when this amount of the matter is so small, even if this is very nonlinear, we know that they just stay constant in time. But as the universe gradually becomes dominated by matter, of course, all these discussions just failed. So this is an interesting kind of area of study, the areas which need to be studied. Okay, but anyway, just apart from this possible nonlinear corrections, one can sort of derive rough but interesting constraints on the primordial CDM isocurvature perturbation, which just actually appeared this morning down with my postdoc, Sam Passagia. So the point is that, as you see, this is the amplitude, which means the amplitude of the initial isocurvature perturbation. It's like 10 to the 4, 10 to the 7, 10 to the 10. So it's very highly nonlinear. But it doesn't matter. It's okay because the matter component is much smaller. It's exponentially very small. But although so it's not so I mean so since we are just ignoring the nonlinear corrections, maybe there are some other maybe a few errors, but still you definitely see this kind of trend to have some constraints, because if your amplitude is, say, if you give some scale and the amplitude of that the perturbation is much greater than this line, then you definitely produce too many black holes. So this is in some sense the first non-trivial model independent constraint on the primordial CDM isocurvature perturbations. Of course, since this is highly nonlinear, probably there are some very interesting secondary effects which needs to be studied more. There are some, by the way, how many more minutes do I have?
Around 10 minutes.
10 minutes, okay. So you may actually form, I mean, this is so that you can sort of form primordial black holes from a cluster of primordial black holes. But here, let me just focus on the case when you produce a very small primordial black holes which have evaporated by today, but they are sort of present very early universe abundantly, so that they sort of temporarily dominate our universe. So this is kind of an early universe, early matter dominated universe model. So in this case, although this curvature perturbation responsible for the primordial black hole formation would have generated another gravitational wave, but the amount of gravitational wave would be smaller than this radiation energy density. And as this matter density, primordial black holes start to dominate our universe, since the radiation energy density becomes negligible, at the same time, all these gravitational waves produced by those curvature perturbations which form the primary black hole, it will become negligible. So in this sense that if nothing happens later, then you would never see any trace of those primary black holes because they have evaporated too early in time. However, when they actually decay, maybe this, during this decay, those oscillations, these adiabatic perturbations produced by primary black holes when they dominate the universe might start oscillating and then start producing gravitational. These gravitational waves actually may be detectable and can constrain all these models. And this is in fact found to be the case. The point is that in the standard sort of say case of constant decay rate, such as the case of the particle decays, the decay time scale is so slow, it's always of order the Hubble. Therefore, this small scale fluctuations will not sort of heal the transition. Essentially, it's an adiabatic sort of adiabatic approximation for the wave is applicable. So there won't be any sort of a new production of anything. It's just slowly start to oscillate and so on. However, if the transition is fast or if this decay rate is not constant in time, actually there is an epoch where this transition can be very sharp. And this sharp transition can lead to very large enhancement of gravitational waves, and which was first mentioned by this Inamata et al. But anyway, the point is that this is indeed the case for the black hole, primary black hole. Sorry, something wrong is here. I think this is just H, and as T goes to T evaporate. Anyway, so and actually this was actually the case, and if you do some simple sort of analysis with some fairly simple approximation like Poisson distribution for the initial black holes and so on and so forth, then you have this gravitational wave power spectrum, which has this k to the 5 peak, the scales like this, and this has a gravitational wave energy density per logarithmic scale of the wavelengths at the frequency scales like k to the 5. Anyway, so this gives rise to interesting constraint. For example, if you consider some particular value of say mass and the fraction of the fraction of the universe which it turns into black hole, then of course it can all reach the advanced LIGO or VISA level and so on and so forth. These are all sort of I mean, details are not so important, but essentially, so you have some if such a very sharply sort of a peaked spectrum is observed, background cosmological background spectrum is observed. This strongly indicate that in the very early universe that there was this black hole dominated era. Or if we don't observe them, then they will give us strong concerns on these scenarios. Of course, there's some very sort of a caveat. The fact is that since the perturbation, for example, Poisson distribution is peaked at this UV cutoff scale, which is essentially the mean distance between the say black holes, and at this mean distance, density perturbation amplitude is almost order unity. And as they grow like in proportion to scale factor, they soon becomes nonlinear. So actually, there are all these scales, all these concerns I talked about assume the simple extrapolation of the linear models, linear theory, and which is probably more or less okay because everything which is very important is this gravitational potential. But still, I guess we need a little bit more work. Anyway, so to conclude my talk, the take-home message is that the primordial black holes may play central roles in gravitational wave cosmology, especially when we talk about those background gravitational waves. So let me just call it the PBHGW cosmology. And the recent sort of studies tell us that they actually maybe all these nonlinear isocurvature initially isocurvature perturbations may play very important roles in this primordial black hole gravitational wave cosmology. Thank you very much.
Thank you. So are there any questions? You can raise your hand or write the question in the Q&A or chat. If you want. So I see that Luca has a question. Go ahead.
Hello. Hi. Thanks for the nice
Hello.
talk. Yeah, can you hear me?
Yes.
Okay, good. So I'd like to ask, like, how much does your analysis depend on the inflationary model? Because I think you just consider a one scalar field, right? Does your study depend if you would change if you would consider different inflationary model?
Well, so this first sort of all this discussion about this standard sort of a conventional scenario, can be a multiple, say, how to say, a field model. So it doesn't have to be single scale field model. So that's one thing, and then about all these the isocurvature models. We don't know, but as I have said, the only thing we sort of assume is that for some reason there were initial isocurvature perturbations, and of course, if we trust the inflationary model, these curvations, series of those curvature perturbations, isocurvature perturbation must be say embedded in the model, inflation model, but at the moment, we don't have any concrete model apart from this is a very specific, say, cue-ball type scenario. We don't know, but there are many interesting. By the way, maybe I have just shown one interesting. This paper by Flores and Kusenko about a year ago. So they consider some very alternative strong force. It's like fifth force, but which can be very, very strong. And of course, so it cannot be the one which dominates our universe today, but it can affect the early universe physics. And if you have this very, very strong, say, let's say scalar gravity, then those strong scalar gravity can enhance the collapse. Yes. So that's an interesting thing. And maybe, so if you just give some specific kind of model, it can be considered as an alternative gravity model. As Alessandra said, that maybe you can constrain such model from these black hole mergers and so on and so forth. But anyway, so for the isocurvature scenario, we don't have any specific models at the moment.
Okay. So yeah, because as a second question, like if it's because as you said, so you want to use gravitational waves like to see primordial black holes, but like the inverse question could be like once we confirm primordial black holes, then maybe we can use primordial black holes in principle to test in some way like some inflationary model.
Oh yes, that's for sure. Yes, that's right. Yeah. That's right. And actually that's why I mean it's one of the things which was important, as you said, is this dependence. And if you take so log of beta, then I mean it's also sigma square only depends on logarithmically on beta. So if you observe beta, which means that if you observe primordial black holes today, then we can constrain the model about that, which not so tightly. So you do have some freedom to play with. So that's a good thing for us. I mean, eventually we should know the detailed sort of production rate and everything, but which probably would be not given simply by this power spectrum. You need it's like formation, like astrophysical black holes. So you have lots of parameters, lots of parameters which determines the amount of black holes. So in the end, if you try to make it more and more quantitative, yes, you have to arrive at that kind of stage. But at the moment, and I probably for the next decade or so, I guess more or less this is okay. So, and it's just interesting enough.
Okay, thank you.
So I suggest that we leave so there's other people that want to ask questions, but since we are supposed to have a discussion session right after, and we are a bit late because, well, Rainer took a bit more time because he will not participate in this discussion session. I think we can have these, well, I can confirm with the organizers, like have a 10 minutes break now, and then we have a 20 minutes discussion to keep on track.
Sure, it's fine.
Okay.
Okay.